the Cartesian coordinate system. The goal of this video is to learn how to represent vectors in 2 and 3 dimensions respectively. So we begin with the 2-dimensional representation of vectors. Now we have a rectangular axis or coordinate, as we call it, this way. So this is the positive x-axis, this is the negative x-axis, this is the positive y-axis, and the negative y-axis. And of course these two axes meet at a point called the origin, 0, 0. So we know already from the previous video that in the x direction we can define a vector called a unit vector. That is a vector of length 1. So that is a unit vector I in the x direction. We can also define a unit vector j in the y direction. So we have here j is a unit vector in the y direction. Of course that can be defined also on the negative x and y axis respectively. Now what does this unit vector do for us? Now on the x-axis, for example, we can represent any vector on this x-axis as some product of the unit vector. Okay, so for example, if we have a vector say a, and that vector is just has a length 2. Now if this vector lies on the x-axis, we can write this vector as a equal to what? 2i. So 2 times the unit vector I. So this tells us exactly the direction, or on the axis, it tells us the axis rather, where vector a lies. So when we see 2i, this simply means that this vector a has length 2 and it is in the x direction, since I is a unit vector in the x direction. Of course, unit vector means that the length of this vector is 1. Therefore, if the length of the vector is 1, so this simply means 2 times 1, which is just 2. Likewise, if we write say b, vector b equal to say 3j, 3 times the unit vector j. This tells us again in what direction exactly this vector lies. So this means that vector b with unit 3 is a vector with length 3 in the in the positive y direction, because the unit vector here j is a unit vector in the y direction. So that is just what happens there. Now with this knowledge, with what I've said now, we want to now learn how to locate a vector on this 2-dimensional coordinate system. Now for instance, if we have a vector, if I given a vector, say vector a now, with coordinates, or rather with a vector a as 2i plus 3j, we want to locate this vector on our plane, or on this system. So this simply means that this vector is 2 units to the x in the x direction. So because 2i, the I here already you know what this means, and 3 here means this vector is 3 units in the j, in the x, in the y direction. I beg your pardon. So what does that mean here? Let us come back here and represent what that means. So 2 units in the x direction is this. So unit vector is 1, so this is 1. So 2 must be somewhere here, kind of. So this 2 is from the origin to this point, other point, point 2. And this vector a is 3 units, in the positive y direction. So this is 1, unit vector is 1, so 1, 2, say 3. So the point 3 is somewhere here. Now, the vector a is now located at the point where 2 and 3 will meet. So what we do is at the point 3, we draw a line that is parallel to the x direction. So that line is this, parallel to the x direction. And on 2, we draw another line that is parallel to the y axis. That line is parallel to the y axis. What do we observe? Those 2 lines meet at this point. Now this vector a is the vector is the line from the origin to the point of intersection of these 2 points. That point there. So the vector a is located at this point. So vector a is the vector from the origin to this point where 2 and 3 meet. So I can write this vector a here as 2i plus 3j. Okay. Now we can also write this vector in what we call coordinate form, in terms of coordinate in pairs of coordinates. So you can still write vector a here, vector a as the x coordinate is 2, so 2, the y coordinate is 3, 2, 3. So going forward, we try the understanding that if a vector a is written as 2i plus 3j, this also means vector a equal to 2, 3. And this pair is ordered in the sense that the first coordinate of this pair, represents the movement in the x direction, while the second coordinate of this pair represents the movement in the y direction. With that, this means that if you write this as 3, 2, it will have a different meaning from this. So the vector A is not a vector from the origin to this point. So the length of this arrow from 0 to where vector A is, the length of that is what we call the modulus, or the length of the vector A. So vector A, so we can calculate the length of vector A. So vector A, the length of vector A, which is called the modulus or magnitude of vector A, is equal to what? Now what do you see? Now from here to here is 2 units. Is it not 2 units? From here to here is 3 units. So from here to here is also 3 units, since it is a rectangle. So, and this forms a right angle, triangle, and with right angle at this point. So we can apply the Pythagoras theorem, to find, the value of the length of A. So if we apply that, what's the Pythagoras theorem? That the square of the hypotenuse is not so. The square of the hypotenuse is equal to what? The sum of squares of the other two sides. So this other side, the square is 2. So we have here 2 square, plus this other side, the square is 3, plus 3 square. So with that, the length of vector A will now be, the square root of 2 squared plus 3 squared. And that will give us the square root of 2 squared is 4, 3 squared is 9. 4 plus 9 is 13, the square root of 13. Therefore, the length of vector A, or the modulus of vector A, or the size of vector A, is equal to the square root of 13. Meaning that if you measure the length of this arrow, or this line, if you like, of this vector from the origin to this point A, what you get there is 13 what? Units, whatever it is. So that's how you locate a vector on a two-dimensional coordinate system. Let us take another example so that we understand better what I'm saying. If I have a vector now B, and then vector B is 4i minus 3j. So how will we locate this vector on our two-dimensional coordinate system? Now, how do we even know that it has to be two-dimensional? Because we have I and j, just two directions, the x direction and the y direction. So that tells us already what we want. So here we have our coordinate system again. We have here, okay, so as usual, our x direction, our negative x direction, our y direction, and our negative what? Y direction. And of course, our origin 0, 0. So the vector B equal to 4i minus 3j. So the x direction is 4 units in the positive x direction, because this is plus 4. So this is, so of course we can still define our unit vectors if you want. This is I, of course this is j, and that can be defined also on this other side, I, and of course here is j, unit vectors. So 4i, 4 in the positive x direction, so 4 should be somewhere here. Let's just call that point 4, and negative 3j. So this is, so here we have minus 3j. So the vector, so this point here is to the negative, y direction. This is minus 3, so negative y direction, and of course j again is a unit vector. So minus 3 we see somewhere here. Okay, so that is a minus 3. So we want to now locate the point in space here where this vector B should be. So what do we do? As usual, at this point here 4, we'll draw a line that is parallel to the negative y, or to the y direction. So this line here is parallel to the y direction. At the point minus 3, we draw another line that meets this line but parallel to the x direction. So that line is this, parallel to the x direction. And once again, the two lines meet at this point. So the vector B now is, and I want to draw a line from the origin to the point where those two lines meet. So that's the point. So at this point, we can locate our vector B. So vector B is here. And what is vector B? Vector B is given as 4i, okay, minus what? 3j. And of course, in terms of coordinates, we can see that vector B to have the coordinate 4, what? Negative 3. Where 4 here represents the units in the x direction, and minus 3 represents the distance in the y direction. Okay, so as usual, the length of this arrow once again represents the length of the vector B, or the modulus of vector B, or like we say, the size of vector B. And once again, we can determine what that size is. From what we did in this in the previous example, it's obvious that the length of a vector A, here we had the vector was A equal to 2i plus what? 3j. Now we observe that the length of this vector A is simply the square root of the sum of the squares of the components. The x component is 2, and we had here 2 squared, plus the y component is 3, we had a 3 squared, and we had all of them, under the square root sign. So this simply means that, in 2 dimensions, the length of a vector B, of this vector B, also would be the length of vector B is equal to the square root of the sum of the squares of the components of vector B. Now the x component of vector B is 4, so that is 4 squared, plus the y component of vector B is negative 3, so plus minus 3 all squared. If we compute this, we're going to have the square root of 4 squared is 16 plus 3 squared is 9. Okay, so the square root, so that becomes the square root of 16 plus 9 is 25. That is equal to what? 5. Therefore, the magnitude, the length, or the modulus of vector B is just 5. Okay, so this is how we represent vectors in 2 dimensions. We'll now go over to representing vectors in 3 dimensions and see the beauty of it. So 3 dimension. Now, unlike the case of the 2-dimensional coordinate system, it is quite difficult to visualize the 3-dimensional coordinate system on paper, and that is because we try to represent 3 dimensions on a 2-dimension space. Okay, so this paper here is 2 dimension, it has a length and a breadth. So this is a 2-dimensional system, so we try to represent a 3 dimension here. Now, but the striking thing here is that in 3 dimensions we define a third length, which is the height. So you look at the space, your room space, as a 3-dimensional object. So now in 3 dimensions, we're going to have an additional coordinate, like I've said already. So here we have something like this, whoops, and this. Very good. So here we have here our x direction or x axis, we have here the y axis, and we have here the z axis. And of course, once again, we have our origin 0, 0, 0, where the 3 axes meet. And we can also define, as usual, our unit vectors in each of these directions or axes. So in the x-axis, we can define as always a unit vector called vector I hat. And in the y-axis, we can define another vector called the unit vector, vector j hat. And of course, in the z direction, we can define now a new unit vector, and that will be vector what? K hat. Like you already know what these unit vectors will do. We can write any vector on this axis as some multiple of the unit vector. Okay, so just like we had in the 2-dimensional case, this 3-dimensional dimensional vector 2-dimensional coordinate system also has the negative of the axis. So this is the positive x-axis, so the negative x-axis will point in this direction. So that would be the negative x-axis, so this is minus x, and the negative y-axis will point in this direction. So that will be our negative y-axis, and of course the negative z-axis will point in this other direction. Okay, so when we try to represent vectors using this 3-dimensional system, we should also be aware of the fact that these axes also have their negative parts. So I'll just draw this again, but now without the negative parts, and make a few comments. So once again, we have here our x-axis or direction, the y-axis, and the z-axis, and of course the origin 0, 0, and the unit vectors I love these vectors. It should be j, beg your pardon, because the y direction, this is the x direction, so vector I hat, and of course now a new unit vector in the z direction, which is vector k hat. Now what we see here is imagine your room. Just take a look at the corner of your room right now. You see where 2 walls meet, where 2 walls meet. You look up, then look down, to that very down corner. Now what do you observe? You see this is the floor. Look at this as the floor where you are, okay? And look at this as that space, that divides the 2 walls. So here is one wall, is another wall, and here is the ground where you are standing currently. Okay, so it's quite difficult to visualize 3-dimensional vectors on a 2-dimension, on 2 dimension. So, but that is how you look at it. This is the floor of your room, and then this is the floor corner of that room, and then up there, which takes you to the ceiling of your room, this is one wall, and this is another wall. Okay, so that is what we are doing here. So here is the x direction, the y direction, and of course the z direction is what defines the height of your room actually. So how we look at this is look at the right hand rule. Okay, look at it this way. So this is your room and this is the corner. So we look at, you see that the floor, so this is the floor. So the floor is this. So this is the x-axis, okay, the y-axis, and then the z-axis is this one that points, that points up. So the system is like this. Very good. Now, it's obvious that between the x and the y-axis, the floor, the angle between these two axes is clearly what? 90 degrees. Then the angle between the wall, this right wall, and the floor again is 90 degrees. You can look at it right now with your eyes. And of course, the angle between this left wall and this x direction, once again, is a 90 degree. Very good. What we now want to look at is how do we locate vectors now on this three-dimensional coordinate system, just like we had done in the two-dimensional case. So we shall take one or two examples to illustrate. So example 1, we wish to locate the vector A, which is 2i plus 3j plus 5k on our coordinate system. Now the first thing we observe is that this vector has three components. Okay, so we can write this as 2, 3, 5, with the understanding that 2 simply means it travels 2 units in the x direction or positive x-axis, 3 units in the positive y direction, and 5 units in the positive z direction. Okay, now since we have three components of this vector, this means that we can only locate this vector on a three-dimensional coordinate system. Is it not so? Second observation is that we see also that the coordinates, they are all positive. So the x here is 2 positive, y is 3 positive, z is 5 also positive. So what does that tell us? That tells us that we might not be needing the negative parts, the negative sides of our coordinate system. So we'll just stick to the positive parts of it alone. With that said, I'll now draw the following. So I have here, okay, I hope this is good enough. Good. All right. Okay. All right. So this is our x direction, y direction, I beg your pardon, that should be y. This is our x direction. I'd like you to stick to this rule: x direction, y direction, and of course here is our our positive z direction. Do not forget that these vectors meet at the point called the origin 0, 0, and we can define our unit vectors if we want. I wouldn't want to make my diagram too clumsy, so I'll just forget about the unit vectors, but I hope you understand that they are there. Very good. Okay, with that said, let's now locate our point. I like to just calibrate this axis for clarity sake. So this is 1.1, this is 2, called here 3, so here is 4. All right, so in the x direction, this is 1, this is say 2, this is say 3, this is say 4, and say 5. Of course it goes on and on. And in the z direction, this is say 1, this is 2, 3, say 4, 5, and 6. Okay, now we start. Vector A, in the x direction, we have what? 2 units in the x direction. So 2 will be, this is 0, so 0 to 1, so 1, 2. So 2 is somewhere here. That is where 2 is. Now in the y direction, 3 units. So 1, 2, so 3 is somewhere here. Now before we put up we mark the z direction, we have to first find the intersection, of these two axes. So that will be on the floor, okay, on the floor. So what we now do is, from this point, 3 on the y direction, on the y axis if you want, we now draw a line that is parallel to the x direction, So I'll just try to draw this like this. So parallel to the x direction is something like this. Okay, I hope it's nice enough. Very good. So, and on the x direction here, from the point 2, we draw another line that is parallel to the y direction, but that meets this other line. So we draw a line here parallel to the y direction. Very good. These two lines meet at this point. Okay, these two lines meet at this point. Now, from this point of intersection of these two axes, we now take the x the x unit, which is 5 in the x direction, in the z direction, I beg your pardon, because it is 5k, so 5 in the z direction. Now from here we take 5 units up, because this is positive z direction. If it was negative, we'll take it down. So 5 units from here will not be at 5, would be at what point? We're already at 2. So that 2, from 2 to 1 is 1 unit, 1 to 0 is 2 units, so 3, 4, 5. So 5 will be at 3, at the point 3 on the z direction, on the z axis. I hope you understand what I'm saying. Let me say it again. We've intersected the two axes, x and y axis, at this point, which corresponds to 2. Corresponds to 2 here. So when I want to move 5 units towards the z axis. So from this point, I am saying that 5 cannot be at this point, cannot be here, okay, even though this is 5 on the z direction, on the z axis. So 5 from here, we're already at 2 here, so 5 from 2 is from here, so we have 1 to the origin, 2, 3, 4, 5, so 5 will be at 3. So from this point, we will now draw our line parallel to the z axis and stop at what point? We stop at 3. We stop at 3. We stop at 3. So our vector A equal to 2i plus 3j plus 5k is ready. And what is our vector? That will be the vector from the origin to that point. So the vector is the vector from the origin here to this point. That is the vector A. Yes. So that's our vector A. So that's vector A equal to 2i plus 3j plus 5k. That is vector A. So we take the x and the y coordinates, okay, and where they intersect, we now take the z, coordinate. And at this point here, the vector from the origin to that point, where the 3 vectors now meet, where the 3 points meet, now becomes where vector A is located in space. With this idea, we can now form what we call a rectangular parallelepiped. Parallelepiped. I hope I got the spelling right. Okay, rectangular parallel. Let's see what this means. And now let's see what happens. We want to now join all the points of this vector and see what happens. Remember, we are going 2 units on the x direction, 3 units on the y direction, and then 5 units in the z direction. So let's see what happens with that. So from the point 3, which is on the y axis, we want to now move 5 units, towards the z direction. So that with 5 units parallel to the z axis, so that from here is 0 already, because this is 0, 0, 0. You will move 5 units from here, we'll land at 5. So that would be, so we'll move 5 units. Oops, I hope I'm okay. Well, let us call that point 5. So we'll land at the point 5. Again, from this other point 2, we'll take 5 units again towards the z direction. So we are at 2. So 5 will be at 3 once again. So 5 would be, so this is 3. So 5 will land us where? Good. 5 will land us there. 5 will land us at this point. What else? From the origin again, let us take 5 units in the z direction, the z direction. So 5 units will take us where? Will take us to 5 from 0. So 5 units will take us to this point. So we are here. So that is 5 units to this point. Okay. Now let us join our axis and see what happens. So we want to join these 2 points. So this will be parallel to the the x-axis, and that will be 2 units. So we are at 4. So this is 3. So 2 units will be to 5. So we join this. We join these 2 points. Good. We'll join these 2 points, which will be parallel to the y direction. Okay. So we now join these 2 points. Good. We now join these other 2 points. Join these 2 points here, and then join these other 2 points at the top. Join these 2 points. Whoops. And what do we see? We see a picture of a rectangular parallelepiped. Wow. And this looks like the shape of some room or some box somewhere. So I guess you can now see you can now see the picture of your room, what I was talking about initially. So this is the point I was talking about. See it here. So this is the floor of the room, okay, and these are the 2 walls of the room, wall number 1 and wall number 2. So with this, we can, you now see why it was difficult to visualize a 3-dimensional vector on a 2-dimensional plane, okay. But this is just a little, I think there's a little beauty now with this. So with that vector 2i plus 3j plus 5k, we have been able to form what we call a rectangular parallelepiped from the vector A. So once again, the length of this arrow from here to here, that length of this still defines the magnitude or the size, or what you call the length of our vector A. And like we did in two-dimensional case, here also the length of vector A or modulus is equal to the square root of the sum of squares of the three components of vector A. So the first component is 2, the x component, 2 squared plus 3 squared plus what? 5 squared. And that is the square root of 2 squared is 4, 3 squared is 9, 5 squared is 25. That gives us the square root of 4 plus 9 is 13, 13 plus 25 is 38. So the square root of 38 is the length of vector A. Okay, we'll take a second example to also just to emphasize. Now I want to locate the vector B, negative 2I plus 3J minus 4K. Okay, so this vector once again it will be on a three-dimensional coordinate system. Why? Because it has the x component, y component, and the z component. However, we'll notice here that we'll be needing the negative x axis. We'll also be needing a negative z axis. So you should recall how our axis look like this. Okay, if you recall, this is how they look like. So this is positive x axis, this is a positive y axis, and positive z axis. So we have here negative z axis, and this is our negative x axis, and our negative y axis. So I want to just put down the axis that we need. So here we need negative x axis, which is this one. Okay, so we'll be needing, so this is the origin. I call this point my origin. So we need the negative x axis, which is that. So this is our negative x axis. What else do we need? We need a positive y axis, but this is plus 3j. So we need a positive y axis, which is this axis here. So we go this way. So this is our positive y axis. Very good. What else do we need? We need a negative z axis, and negative is down. So negative z axis is somewhere, is down like this. Okay, beautiful picture. This is our negative z axis. Very good. So here remains our origin 0, 0, 0, the point where the three axes do meet. So like before, I'm just going to calibrate this for us to see what is happening. So here I call here 1, call here 2, say 3, say 4, say 5, and here say 1, say 2, say 3, say 4, say 5, and down here I have here negative 1, negative 2, negative 3, negative 4, negative 5, and of course it goes on and on. So as usual, you can define on each of these axes you can define the unit vectors I, j, and k. Okay, hope that is already clear. So let's look at our vectors now. Our vector B rather. So vector B on the x direction, which is negative x direction. So this is negative if you want. This is negative x direction. We have minus 2 units. So minus 2 is at this point. That's minus 2. And then the y direction, we have 3 units. So this is y direction, positive y direction. We have 3 units. So 3 is somewhere here. So like we did before, we are going to first know where these two axes meet. And from that point of intersection, we'll get the z coordinate. So from this point, we now draw a line here that will be parallel to the y-axis. So we draw, that's good, yes. And from this other point here, we'll draw another line that is parallel to the negative x-axis. So that will be something like this. Very good. Now these two axes meet at this point. So from this point, we're going to now take the z coordinate, which is minus 4. As we did before, we're already at minus 2 here, at minus 2. So minus 4 will not be at minus 4. So minus 4 will be, this is minus 2. So from here, minus 2 to minus 1 is 1 unit, to 0 is 2 units. So we have here 1, 2, 3, 4. So minus 4 will be at the point minus 2. Hope you understand what I mean. We are here. We're already here at minus 2. So we're taking minus 4 units downwards. So that will be from minus 2 to minus 1 is 1 unit. Minus 1 to 0, 2 units. 0 to 1, 3. And minus 1 to minus 2 is 4. So from here, we're going to stop at the point negative 2 at this point. So we'll now draw a line from here, good, to the point minus 2. To the point minus 2. So we have located. So that's where minus 4 is. Now where then is the vector? Vector B. vector B now becomes the vector from the origin to that point. So I want to draw it this way. So from the origin, whoops, that's nice. So that's vector B now. So that is vector B. That's our vector B. So vector B has been located. So vector B here is vector minus 2i plus 3j minus 4k. That's our vector B. Like we did before, we also can form what we call a rectangular parallelepiped from this vector, or from the sides from this vector. So let us see how we do it, just like we did before. So from the x-axis, minus 2, we are here, that's minus 2. We'll take minus 4 units towards the negative z-axis. So we are here, so minus 4 will take us again to minus 2. So minus 2 to minus 1 is 1, minus 1 to 0, 2, 0 to minus 1, 3, minus 1 to 2, minus 2, 4. So from here, we draw 4, we go 4 units to the negative x direction. That will be somewhere here. So we go 4 units. Whoops, that's good, to that point. 4 units. We now go to the y-axis, which is 3. We are here, that's the y-axis. Where are we now? This is the y-axis 3. Okay, 3. So here we move 4 units in the negative z direction. 4 units in the negative z direction. So we are, this is 3. We are at 0 there. So minus 4 units will be at the point minus 4. So that will be, so from here we draw, whoops, to the point minus 4. Good. That's minus 4 units. We now move again to the origin, and move again minus 4 units, or 4 units if you like, in the negative z direction. So that will be at the point minus 4. So we move here, whoop, to this point minus 4. Very good. To this point minus 4. Then we can now join up our points. So from here to here, we'll draw a line that is parallel to the negative x-axis. So that is this line, that is this vector here. And of course, you see that this vector will be minus 2 units, because from minus 2 to minus 4 is 2 units. You see, it's obvious. And then we don't join this other vector here, which is parallel to the y-axis, and that vector will be 3 units. Let us see. This is 0 to 3 is 3 units. So we see it there, so it corresponds. So that is a vector we join there. We now join again another vector here, or another line if you like, that joins this point, and that is parallel to the negative x-axis, and that will be 2 units again. Let's see. Here is what? Here is 2, minus 2, here is minus 4. So again, 2 units, we join. Finally, we join these other 2 points here. So we join these other 2 points. Whoops. And what we have again is a rectangular parallelepiped. So the length of this arrow from the origin to this point B, once again, which we denote as the absolute value of vector B, is the length of vector B, which can be calculated. So the length of vector B is equal to the square root of the sum of the squares of the components of vector B. What are the components? The x component is minus 2, so minus 2 squared, plus the y component is 3 squared, and the z component is minus 4 all squared. So that becomes the square root of minus 2 squared is 4, plus 3 squared is 9, and then minus 4 squared is 16. Am I right? Yes, 16. So we add up, we get what? So 4 plus 9 is 13, plus what? 16. And that gives us the square root of 29. So the length of this vector B from the origin to that point is 29, root 29 units. So this vector B, and what's vector B? Vector B is minus 2i plus 3j minus 4k. That's vector B. Or you can write vector B in terms of coordinates as negative 2, 3, and negative what? 4. So going forward, if we write a vector as with if we denote a vector with this coordinate, this also implies this. So, but for shorthand notations, we usually will write a vector B in terms of its coordinate, minus 2, 3, and minus 4. So with this, you can, sketch just about any kind of vector, any vector according to the coordinate system. Of course, we have higher dimensions of our coordinate systems, but, on paper, we can only try to visualize the 2-dimension and 3-dimension vectors, okay? So as an exercise, you can try this for yourself. You may want to sketch this vector in 2 dimensions, 2i plus say 6j, and then vector D, you can try say minus 2i plus say 3j. Number 2, for 3-dimensional vectors, you can try vector E with the coordinates 4i minus 3j plus 2k, and see the beauty of it. And of course the final one, vector f, you can try negative 2i, negative 3j, and negative 4k. Okay, and for these two cases, try to sketch the rectangular parallelepiped that it forms. Okay, I hope you understand now how to represent vectors in 2 and 3 coordinate systems respectively. Please do leave a like on this video, comment, and also subscribe to my channel if you've not done so already. Thank you, and see you in the next video.